I'm going to talk a lot about nitrogen. I'm going to keep coming back to that today. It's the fertilizer that's necessary to grow plants. So in order to produce anything, we have to have nitrogen. But it's also the most common gas in our atmosphere. The atmosphere is mostly nitrogen. It takes huge amounts of energy to pull the nitrogen out of the atmosphere, convert it to a form that we can actually use it, like to make fertilizers, and then once we've used it, we tend to lose it all over the place. It's kind of a leaky thing. And once it's back out in the environment, it tends to cause more problems. So we've got to figure out how to do a better job managing our nitrogen, because the source of energy that we use to get that nitrogen out of the atmosphere is going to be going away, therefore potentially the end of food. And we don't want that nitrogen floating out in the environment. We want it where we want it, when we want it. And then this last one, which is kind of the topic that'll drive this conversation, is climate change. And that is what's happening with our climate systems in terms of destabilization. We've come to the point that we've developed the agricultural systems, we've developed economies on the basis of the type of climate that we have, and that's really important. As we've put more chemicals, nitrogen, and fossil fuels up into the atmosphere, we're changing the dynamics that drive our climate system, and that could bring us some issues in the future. That's kind of the essence. Just a couple cool pictures on nitrogen. That's what it does when it gets away from us. Those are not good things, so we need to do a better job. Another one, and one very rarely that people talk about, is we always talk about these kind of dangerous places in the world where we get our oil, and everybody's worried about national security because of the Middle East and Central Asia is where we get our oil. Where do we get our natural gas? From basically those same places. We do get a little bit of it out of Alaska and Canada that comes into our region, but by and large, for the product fertilizer that we need to grow our food, we're basically dependent on the largest sources and the cheapest sources of nitrogen from those same really kind of dangerous areas of the world. That's an important thing to keep in mind. So a little bit about climate change and what it really is. We have this atmosphere that sits around us, and there's lots of different things in the atmosphere, including nitrogen, but also water vapor, greenhouse gases, other types of things that are up there that create essentially a blanket around the world. And if you've ever gone and opened the car door on a really hot day and gotten into the car and the car is just sweltering hot, that's a greenhouse effect. So we know what this is, and the fact that we have an atmosphere around us with greenhouse gases is a good thing, because otherwise we'd be like Mars or like Mercury, where parts of the day it's just way too hot and then parts of the day it's way too cold. So having these greenhouse gases in the atmosphere enables some sunlight to come through and then bounce back and forth as heat to warm up the atmosphere to a point where we can actually survive on the planet. We can grow crops and things like that. The problem is that's a delicate balance. If you don't have enough greenhouse gases, that sunlight and heat just radiates right back out. And if you have too many, it holds it in too much and it becomes like having an extra blanket on. And that's essentially what we're dealing with. And so some of the greenhouse gases we're concerned with: carbon dioxide, which is what we breathe out, nitrous oxide, which is really important from agriculture, and methane, which is really important from agriculture. And on the very first page I had that picture of the globe with the green. That's methane, captured by photo by NASA. Okay, so a lot of people say, well, there's lots of things that control temperature in the world. How do we know it's actually greenhouse gases that are causing increased temperature, or global warming, if you will? So basically what we have here is, this is from 1900 to 1990 the tracked temperature averages on the planet. This line here is computer modeled temperature averages on the planet. So somebody took a computer and built a model that said, we're going to consider all these different forces that drive temperature, drive climate regulation, and we're going to predict what would have happened. And you can see they do a pretty good job. It's not perfect, but it's a pretty good job. And you know, most of the models that are out there, there's 30 different models that they use to simulate climate, all do a pretty good job of modeling the past. So then what we do is we take those models and we model the future to project what might happen. And you can see there's a number of different drivers. So sulfates, volcanic, ozone, solar radiation, and greenhouse gases. And what's really important here is if you take out greenhouse gases from these equations, these models would actually predict that we would have seen cooling over the last 100 years. Now, this is not a lot. This isn't like it's 10 degrees hotter. It's just very marginal amount. But that very marginal amount is affecting a very delicate balance. And so we're going to talk about how some of that has been or will affect the issues that face agriculture in this state. Okay. So we got to talk a little bit about carbon in order to understand what's driving the fact that the greenhouse gases are going up. There's carbon all over. Most of it is secured away in the oceans. A little tiny bit of it's in the atmosphere, a lot relative to the atmosphere and fossil fuels, but then our terrestrial systems, our soils and our vegetation have about half of what is in that fossil fuel pool, but about 3 times what's in the atmospheric pool. And this is what's happening. On an annual basis, we burn fossil fuels, we change land use, that's mostly deforestation in the southern hemisphere, like the Amazon. And we put up about 8 gigatons or 8 billion tons of carbon dioxide every year. And then vegetation and soils, when plants take sunlight, they suck in CO2, fix it as photosynthesis into plant tissue. That creates carbon that's stored, and then some of that carbon cycles back every year as we eat it or it just decays. Some of that stays in the soils. But about 2.3 gigatons comes out every year. And there's similar processes, it's not photosynthesis, but there's similar chemical process in the oceans where they take out about that much carbon a year. But you can see, and if you've done any kind of budgeting, you can see we're only taking out about 4.6 gigatons of carbon every year, and we're putting up almost 8. So that means every year, and this data is probably 5 years old now. Every year we're putting up a little over 3 gigatons more than we take out. You start to add that up, and when you're only starting with 750 gigatons, in 10 years you've added that, and now you've got 780 gigatons in the atmosphere. So you're adding that extra blanket into the atmosphere, which is the source of concern. Okay, and let's just look at food. How much does food contribute to these greenhouse gas emissions in the entire globe? EPA tells us that around 6% of emissions from the U.S. come from agriculture. Well, that's not too bad. Most of it comes from transportation and other energy uses. But globally, about 12% of emissions come from agriculture. But then if we say, well, agriculture isn't just growing food, it's all the transport, processing, cooking at home, storage at home, these kinds of things. All of those things require energy. All of those things have emissions. And so when you look at it, there's a couple of different estimates that say if we include the whole concept of what it takes for society to eat, as much as 35% of all the emissions are associated with food production and consumption, and that's not insignificant. So it's an issue that we've got to address. Now, it's also an issue that we can't ignore the fact that we have to eat. So there may be a time at which we say we can do a little bit to reduce our emissions from the food system, but we may need to look elsewhere to really reduce emissions because we can't stop eating. Okay, so we have this project called Climate Friendly Farming, which was funded about 8 years ago by the Paul Allen Foundation, and they gave us $3.75 million in 2003. That was why I was originally hired. And since then, we've had about another $44 million in research funding that we've been awarded. So a very, very, very prominent program. But the concept here was, well, let's look at agriculture, specifically production agriculture, and the kinds of agricultural systems that matter in Washington State. So we looked at dryland grain farming, irrigated row crop, field crop type farming, and then dairy farming systems. And each of these systems has greenhouse gas emissions. Each of these systems can store carbon in soils, so it can pull more carbon out of the atmosphere, put it in the soils. And then there's this whole other arena that we can take organic matter, things that we grow on the farm, and actually turn it into energy and maybe use that energy to offset fossil fuels. And so that's kind of the concept behind the project. And here's some results, and I'm going to go really quickly through these. Basically what this says is, can we store carbon in our agricultural systems in our soils? And the answer is yes. Some of these systems are pretty good. We can store quite a bit of carbon. Other systems are not so good. So the one that's probably most relevant to Othello is this one, Patterson reduced tillage. That's a potato production system, very similar to what you'd see here. In fact, we started by modeling at Othello rather than Patterson, but we ended up going to Patterson because we had the data we need for corroboration. But basically, by reducing some of the tillage in that system and reducing some of the oxidation of that carbon, we could store carbon in that system. That's a good thing. And the difference here, and it doesn't really matter, is this was kind of using a low estimate and that was using a high estimate. So that's a good thing. We know we can do this, and the best part about it is reducing tillage reduces fuel use, reduces cost. So the question is, can we do it and maintain quality and yields and those kinds of things? Second one, I talked about nitrogen. We don't want nitrogen out in the environment. Well, nitrous oxide is one of those things that gets out in the environment, goes up into the atmosphere, and it's this really potent greenhouse gas. And there's an intergovernmental panel of scientists that has done a lot of research on climate change, and they've basically said about 1.25% of all the nitrogen you apply will go up into the atmosphere as nitrous oxide. And so these bars, this is all the same systems that we were looking at, dryland grain farming, irrigated potato production, that kind of thing. These bars represent what that 1.25% would be. These other bars represent our findings from actually doing field research and then modeling that field research on the production systems that we use in this state. And what that tells you is we're doing a really good job relative to the average in managing our nitrogen, because we don't have that bad of emissions. Probably the most interesting one, back to the potato system in Patterson. We don't have hardly any emissions compared to what you would expect based on the averages in the science. The reason for that is because we use fertigation. So we put a little bit of nitrogen on at a time. And we put a little bit of nitrogen on, the plant takes it up right away, doesn't let it go to the atmosphere. That's a very good thing. We need to figure out more ways to actually fertilize in such a way that we don't lose nitrogen, because it saves us money, it saves us energy, and it reduces our emissions. One of the things that we've done a lot of work on is using some, call it space age technology added to farming. This particular farm is in Pullman, and what we've done here is, it used to be that if you had a field of wheat, you fertilized at the same rate across the entire field. But we know that our yields are not the same across the entire field, because there's things going on in that field. In some places that yield may be 4 times as high as another place in the field. So if we expect yields to be 4 times higher in one spot than another spot, why do we fertilize them the same? So, but there's technology now, GPS, GIS, variable rate fertilizer applicators, lots of different technologies that are out there that if we put them together, we can actually change our fertilization patterns. And we can predict that in this spot in the field, we know we're going to get a really high yield, so let's put a lot of fertilizer there. But in this spot in the field, we know we're going to get a really low yield, so let's not put as much fertilizer there. And the technology is there to do that. What we've been working on is building what we call the decision support, or essentially the software to drive the system. And what we've shown is, in this particular grain field operation, about a 20% reduction in fertilizer applied and get the same yield. The cool thing about this one is in less than a year, you'll actually pay for the technology. And it could save a lot of energy if we did this across 1 million acres. That's probably more substantive than any other kind of energy change that we could make in our dryland agricultural systems. I think if you're interested in agriculture and interested in production agriculture in the future, you got to be paying attention to this stuff. You're going to have to get smarter and smarter and smarter and be able to deal with these kinds of technologies. Just real quickly, you're going to have a smartphone, because a lot of what we're doing now is going to come out in smartphone apps in terms of prediction, those kinds of things. So I'll say this is not my grandpa's farm anymore. So what this is, and this is just kind of another way to look at the whole farming system, is we change our management. We can look at this system and say, there's all of these factors. We have carbon sequestration, we have emissions that come from the farm, we have fuel that we use, and all of these things. What is the total impact of that entire system? And if we change a system, for instance, if we go to no-till, if we start using some of that precision nitrogen, how can we improve that whole system's carbon footprint? And that's what this shows. And what it shows is there are some potentials, depending on the system, to really reduce our overall carbon footprint. And we'll never get it perfectly carbon neutral, because it's never going to happen, but we're going to come close. I'm going to switch gears a little bit now and talk about some of the work we've done in bioenergy. And basically what this is there's a lot of materials out there: manures, food processing waste, food waste, trash, forest waste, mill residues, and even field residues that could be turned into oil or something like oil. And so what we did is we went across the state of Washington and we calculated, kind of assessed, what do we have and then what could that mean. And so we started with eastern Washington, and I'm going to go straight to the entire state. And in a second inventory we did, basically if we took most of the waste or underutilized organic material in the state, that's about 50% of the electricity that we use in our houses in the state. That's very significant. Or it's about 1.5 billion gallons of ethanol, which is about 30% of the gasoline we use. So everybody talks a lot about maybe growing crops like corn for ethanol or oil seeds for biodiesel. This blows that away in terms of the total potential.
And this is waste.
And this is, well, it kind of depends. Some of it's waste. Some of it we feed to cows, like cold potatoes get fed to cows. So there will be trade-offs where if we choose to use it this way, we may lose it. Field residues, well, we've calculated them in the context here as their waste, but we really don't want you using field residues, and I'll talk about that later. Or at least not as much. So if we're going to look at carbon sequestration and reducing our total nitrogen demands in agriculture, and deal with this question of energy and trying to produce energy, climate change, we got to start looking at these wastes not just as maybe potential sources of energy, but if after we convert them to energy, there's still something left there. And what's left there tends to be carbon, nitrogen, phosphorus, potassium, sulfur, all the things that we need to fertilize our plants. And so what we've done, and this is a kind of a first run, we need to go back and look at this, is this is similar to those charts I was just showing where everything was above the bar in terms of negative from our systems overall, even though we could sequester some carbon. We looked and we said, what if we took manure and added it to the fields as a new source of organic material? And what it shows is there's actually a couple places that once we eliminate the nitrous oxide emissions from the equation, it's positive that you could actually have a positive carbon footprint, meaning you're actually taking more carbon out of the atmosphere than you're emitting to the atmosphere. That's really cool. Okay, next thing, I said those organic wastes that we could produce energy have a lot of nitrogen and phosphorus and all of these things in them. Here's the number. So in 2001 in Washington State, we used 176,000 metric tons of nitrogen fertilizer. That's this number right here. So there's more nitrogen contained in those organic materials than we import as fertilizer. All we got to do, get it out of those materials into a way that we can actually use it on our farms. Now, we're never going to quite achieve that, but several of these, food processing, municipal, animal manures, make up a good chunk of that nitrogen, and we know we can do that. And so what you traditionally think of when you think of taking those organic materials and making fertilizers out of them is things like compost. But compost is kind of a low quality fertilizer. It's good, but it's not as good as the different types of synthetic fertilizers we use because there's just not a lot of nitrogen relative to the amount of material. It's kind of expensive and it has some other issues. It's a good thing, but we're probably not going to see it in anything other than basic crops or certified organic production. So what we're looking at is kind of next generation soil amendments, where we look at products that we're going to recover from these organic materials through some kind of biological or thermochemical process and convert into more interesting things that look a lot more like the kinds of fertilizers we already use. And so some of them that we're looking at is, this is a pile of dairy manure after we've put it through an anaerobic digester, which I'll talk about, after we've separated the liquid off. And then we did some other work where we took that dairy manure, just the solids part of it, did some additional treatment, and we were growing plants in it. And the cool thing about that is when you try and do it without the additional treatment, those plants die. But when you do this, do that additional treatment, those plants actually work better than peat moss, which is the industry standard in nursery. So that's when we've patented that, and we're working on that. Done some other things. Now you take the liquid off of that dairy manure. There's a lot of nitrogen and phosphorus in that, and we've had probably 8 or 9 different types of technologies that we've looked at to recover nitrogen and phosphorus fertilizers out of the liquid stream. And that's good because we can get it out of the dairies, so there's not nearly as much on the dairies, which they don't need it all, and then put it onto other farms in the types of fertilizers that we know how to use. And then a couple of the other ones that we're looking at, brassica seed meal, so canola. Have you ever seen a canola field or a mustard field? Kind of an interesting plant in that it has some pretty nasty chemicals in it. Nasty chemicals that will kill lots of things. But if we can take that and get those chemicals kind of concentrated, we can actually use those as herbicides and other kinds of pesticides. But we don't really know how to do it very well and predictably yet, so we've got quite a bit of research going on trying to figure that out. And then another one we're looking at is biochar, which by any other name is charcoal briquettes that you would use to cook your hot dogs in the summer. Basically, we can take virtually any kind of dry material. We could take this table, chip up this table, put it in a reactor called a pyrolysis machine. That reactor will carry, or will take the gases and some other things off and produce electricity or other kinds of energy. And then the remaining stuff is basically charcoal. And that charcoal is kind of an interesting soil amendment that a lot of people have been looking at. But the key here is by looking some more specific details on the types of materials that we can get, we can find materials that work for these other more valuable production systems that are consistent and predictable, and we can use them precisely. So I'm going to talk for a minute now about anaerobic digesters. This is probably the first significant bioenergy production facility in agriculture in Washington State. And what this is it's a big tank, and you take manure and you throw the manure in the tank, or you take food processing waste and you throw it in the tank, or you take what you scrape off your plate at the end of a meal, throw it in the tank, let it go, and then microbes will work on that, consume it, and what they produce is methane. And methane is natural gas. Pretty cool. In fact, my kids, for a 4-H demonstration about 5 years ago, took a soda bottle, filled it with manure, a little bit of water, heated it up, put a balloon over the top, filled the balloon with methane, then lit it with a lighter. Pretty cool stuff. And that's what that is. So basically right out here on the top is, as this manure gets turned into methane, it's flaming. And then we take, inside that building is this great big Caterpillar engine, burn that methane, make electricity. Pretty cool stuff. We've got 4 of these operating in the state now. There's several more in Idaho, and a couple of them, there's about 12 of them between Oregon, Washington, and Idaho operating now. About 40,000 cows manure and a whole bunch more food processing waste are going into these. This is big business. So in Pullman, we've built an anaerobic digester for research purposes so that we can try and develop new systems. We've got several different things where we've done looking at nutrient recovery. I already showed those. And we're actually building commercialized nutrient recovery systems to go with that anaerobic digester I just showed. So we're building the first commercial fertilizer plant at a dairy right now. And here's kind of what it means. If we had, on our 135 largest dairies in the state, anaerobic digesters plus fertilizer recovery, about 20% of our state's demand for nitrogen, about 27% of our state's demand for phosphorus would be getting recovered. That's big. And a huge amount of energy and about between 1 and 4 million metric tons of carbon emissions reduction, which is a huge number. But we said, like I just said, electricity is kind of not very interesting to us. So what we wanted to do is we wanted to use that methane for a transportation fuel. And the reason we want to do that is because if we take manure, convert it to methane, use it as vehicle fuel, that's actually the best carbon benefit that we can get over any other kind of biofuel. So we built with Western Washington University, we've built essentially a refinery, just like you would see at a refinery for oil. And they took it, and their students at Western built a car and built an engine for that car and put that gas, and they ran that on cow power. And we're currently building a commercial scale refinery at that same dairy up in Linden. And everybody always asks, well, you do that for big dairies, well, what about everybody else who has a little bit of manure? And so we had a grad student do a design of an anaerobic digester that could be for very small scale or household scale applications, and we built them. And this thing sits right about here. So you could think of it like a dishwasher appliance. So you scrape your plate into the garbage disposal, wash the material into the digester, put your plate in the dishwasher, close the dishwasher up, turn the dishwasher on, and the hot water comes from, or the heat for the hot water comes from the digester right there beside the dishwasher. So if somebody wants to get really rich, come talk to me and we'll set you on the way that you can commercialize this and sell it to Sears or something like that. I talked a little bit about biochar and thermochemical. So most of the processes that we've been looking at are wet processes or biological processes where we use microbes to do the work. Here we're using heat. And so we built a couple of different smaller reactors in Pullman in our labs to take things like this table, chip them up, turn them into energy, create biochar. Okay, so I'm going to shift gears right now, I'm running low on time, talk about climate change as it impacts agriculture. And I'm going to move through this really quickly because it's too much data. But does anybody know what this is?
Well, that's a flood.
You know which flood that is? 2008, Centralia, I-5 running right through there. This is a climate-driven event. Because what you had is you had a whole bunch of snow up in the mountains. It warmed up really quick, and then there was a huge amount of rain, and all that snow came melting really quick, running fast down there. This is the kind of thing that could become more prevalent in the future with a little tiny bit of warming. That 1 or 2 or 3 degrees on average warming globally, this could become a real thing. You know, more frequently. We already see these kinds of things. They could be more frequent just by that little bit of warming. So climate change will add another layer of complexity and uncertainty onto a system, agriculture, that is already exceedingly difficult to manage on a sustainable basis. Okay, so I'm going to show you, this is kind of the worst case scenario. This was some work looking at corn production across the United States under a couple of different climate change scenarios. The bottom one is a worse scenario, the top one is kind of a not so bad scenario. But the left side here is corn yields currently. The right side is, if the climate changes as it's projected, what's going to happen to corn yield? The darker the color, the lower the yield. So you want green, but everything that goes to red gets lower. So it's going to become a point that if you're a corn farmer in Georgia, you may not be a corn farmer in 20 years because you just won't be able to yield well enough. Okay? So that's the kind of concerns. The further south you go, the bigger these problems are going to become. And so we're going to look at Washington, what's going to happen here. So we've projected on a couple of scenarios, and we worked with the University of Washington's Climate Impacts Group to do this. Basically, we're going to see, they predict between 2 and 6 degrees increase Fahrenheit in temperature average for our region. Not globally, this is for our region. And that 2 degrees by 2020, 3.5 by 2040, 6 degrees by 2080. What does that mean? Well, that means the further out we go, the more frost-free days we're going to have. So growing season's going to become longer on average. So the average temperatures in Pullman and Sunnyside, and this is annual and this is in season on the right side, are going to trend upwards. Precipitation. We don't understand precipitation nearly as well because unlike temperature, which has a pretty good stability, you know, it tends to be cold in January, tends to be hot in July. Precipitation, even though we tend to get more in the winter and less in the summer in this region, we get a lot of this. So sometimes we'll get 16 inches, sometimes we'll get 4 inches. And there's just so many variables that play in precipitation that it's really hard to predict. But basically what they think will happen is we're probably going to get a little bit more rainfall or a little bit more precipitation in the future in this region. But it's probably also going to be more of the same kinds of things that we do. So we already have a winter-driven precipitation system. We mostly get our rain and snow between November and April. We'll probably get more of that and even less in those dry months, which is an issue because when do we need the water for agriculture? In the summer. The other really big issue that we're going to face is snowpack. So where does the water come from that runs down the Columbia River that goes into the irrigation canals that irrigates the basin? Where does it come from? It starts in Canada and it comes from snow. Pretty simple. And if you live in a river valley like Wenatchee or the Okanagan or Yakima, a lot of that is straight out of the mountain right through, and if it's gone, it's gone. So as we see warming, especially warmer winters, more precipitation that used to fall as snow will fall as rain. And what happens when it rains instead of snows in the mountains?
We don't know the defect.
It runs right down. So do we get much use out of rain that falls in February?
No.
All right. So what this shows is this is two different scenarios where current versus future snow water equivalent on April 1st. And the reason that April 1st is important is we know if we have enough water or enough snow in the mountains on April 1st, we have enough water for the rest of the year. The darker that it gets, the more change, the less snow that there is. And here's probably the most critical piece. The blue ones up here are the watersheds that we consider snow-dominant mountain watersheds. The red are transition, meaning snow or rain. And the blue, or green, are rain-dominant watersheds. 2020s, we're down to just the North Cascades as snow-dominant. By the 2080s, they're not even snow-dominant anymore. Very significant issue. The projection is basically 50% or every other year we will not have the snowpack that we need. That's statewide. Specific watersheds, it's going to be much more severe than that. So let's look at one of these. The Yakima River already has problems with having enough water. As we showed here, the Yakima Basin is already a low, it's already problematic. As we go forward, we know that about once every 5 years they have rationing in the Yakima Basin. once every 10 years is very significant, and it's very costly economically. So basically, this is the Yakima River's hydrograph right now. The 2020s, less water, less snow melt available at the time when we need it. The 2040s, the 2080s. So more of what would fall that we currently plan on using actually is going to be gone and out to the ocean when we need it. What does that mean? Well, that's complicated. But basically what it means is if you can't get water, you can't irrigate. Now certain people can get water no matter what happens, other people don't get water. So if you're a junior water rights user, what you see here is your yields are going to be substantially affected by the fact that you don't have water every other year. You're going to lose a lot of money. Now, if you're a tree fruit grower and you're a junior water right user, do you want to continue growing tree fruit if every other year you're not going to have water? It doesn't make sense. So all of a sudden your land went from 5,000 an acre down to 500 an acre in value. This is big. This is important. Now, if you're in the basin, you're on project water, you're in a much better condition. But that doesn't mean that you're not going to be affected by it too. Which is where I'm going now. So we're right in the middle of a project where we're working with the Department of Ecology to try and project for the next 20 years what the Columbia River supply and demand situation is going to look like so that they can start working on supply. So we can build reservoirs, we can encase water, we can do things to lose less water or keep it where we want it so that we can use it. We've got, the legislature has approved a $200 million bond to build water storage. So we're working on creating some baseline forecasts for agricultural production in the 2030s, model those forecasts, and then use our physical models to actually try and understand what's going to happen with supply and what's going to happen with demand as things change. So by August, that'll be ready to show. We also have this other new project, which is a $20 million project that USDA just announced, looking at agriculture, primarily wheat-based agricultural systems, and how they might change under climate scenarios. And so we're looking at a number of different sites, and in fact, the center pivot at Othello is one of these sites. So the concept here is look at carbon, nitrogen, water, and energy dynamics under these systems, look at some more interesting changes in management that we can do to these different systems to try and do a better job managing under a climate change scenario.